So for our third example here, we're going to recall the graph from the Königsberg bridge problem and use Euler's theorem to show that the problem does not have a solution. So what we're going to do here is look at that picture we have for the graph and recognize that on that graph we have that all of our vertices are odd. And as a result, because I don't want to use the blue one, I like using the black one, being consistent, but because all have odd degree, we have that we will not be able to find either an Euler path or an Euler circuit. So we do not have a way to go through each crossing the bridge one time. That is, there is a solution based on Euler's theorem. This is the sort of argument he made originally, way back in the mid-1700s, the mid-18th century. And with these things, it's nice to be able to recognize whether or not we have Euler circuits, whether or not we have Euler paths, or if we have none of them. But when we do, as you saw with my stuff there, you get more practice working on these sorts of puzzles. You get better at being able to identify where you need to go to get these things, to be able to find these paths and circuits. But trial and error is more often than not a great way to find errors more than successes. So we're going to finish this section looking at a way to be able to find these things a bit more systematically, a bit more exactingly, a bit more surely, using what's called Flory's algorithm.